All right, so yeah, thanks everyone for coming to my talk on augmented reality for human-robot collaboration. I'll also be talking about using AR for human-robot negotiation when I talk about my own experiment in a little bit. First, I'll give you a little bit of an introduction to who I am, for those of you who don't know me as well. I'll talk about what researchers have been up to in this field. Then I'll give you a little bit of insight of what I've been up to and what I'd like to be up to in the near future. And then I'm going to go into an established paper and do a little bit of a critique and expansion on that, and like how I'll expand on that for my research. So I earned my bachelor's degree in mechanical engineering with an aerospace concentration at Cornell. And so I definitely see myself first as an engineer, mechanical engineer. I started work as a co-op student for NASA Johnson Space Center in Houston. I got to work in both operations and in engineering. And I worked there full time after I graduated as well, doing some fun stuff on pyrotechnics and energy systems and in situ resource utilization. I then went and worked at Boeing as an engineer and stress analyst in Seattle on both the 787 and 737 airplanes. And then I decided I wanted to get into education. So I earned my master's degree in STEM education. I was actually the first graduate of their program at Boise State University. And I got a job teaching at a pre-K through 9th grade school. I got to teach all ages from preschool all the way through junior high. I was a junior high lead. I got to teach engineering and Lego robotics and things like this. And then I decided I wanted to work in higher ed. So I got a job at the Institute for STEM and Diversity Initiatives at Boise State, working with faculty and students on campus and teachers around the region. I really enjoyed that, being in higher ed, so I decided to come here and get my PhD. I started in the 2018 cohort, and I just this fall became a Draper Fellow. My Draper mentor, Mitchell, is actually on the call as well. I also wanted to add that I've been a volunteer firefighter. I've been a competitive bike racer. I earned my private pilot certificate about a year and a half ago. And I wanted to share these things mostly because they all have applications for augmented reality. I think it's kind of interesting how lots of my interests all tie together. So since I've been here at CU, in my first year, I was an RA on an NSF project. We were looking at using technology to get kids more interested in STEM, particularly using sensory augmentation devices to help kids explore their world. And then in my second year, I joined the CAIRO lab, and by the end of this semester, I'll have completed all of my coursework requirements. I've started experiment implementation that I'll talk about a little bit later. Like I said, I became a Draper Fellow after applying for lots of different fellowships. I've written a literature review on augmented reality for human-robot collaboration. And peripherally, I'm also the Anti-Racism and Inclusion Chair for the Computer Science Graduate Student Association. So I'll start off by telling you a little bit about the literature review that I've done. We'll talk about augmented reality in general, some applications for AR in human-robot collaboration, some technical contributions that have specifically been made to that field, and then how evaluation has been done. What is AR? I'm sure you're all pretty familiar with it, but Milgram was one of the first to actually define what it means as an overlay of virtual graphics and virtual objects within the real world. And that's the definition that I've been using. So whether that real world is viewed unobstructed or partially obstructed or through some sort of intermediate display, the AR features are placed over those real world images. And then my focus is on the topics of AR as applied specifically to human-robot collaboration. So this excludes things like virtual reality or augmented virtuality or things like this. I do explore how it's applied to different types of robots You'll see some examples throughout. And then I conducted this review by searching in common conferences where these kinds of topics are presented, like HRI, IROS, RSS, and so forth. You'll see those noted throughout, as well as their associated journals. And I dove more deeply into reference sections, of course. And I did leave out things that were shorter, like posters or abstracts. These are primarily full papers. So a little bit about AR. It comes in many different forms. The main forms are listed here. So we have head-mounted displays, which are like the Microsoft HoloLens on the left or the Magic Leap on the right. These are kind of the primary ones that people use right now. There's mobile devices. So you might think of a mobile app feature where you can place an item in your home, things like that. You can see this. We'll talk more about the paper that this photo comes from in a little bit. Projection. So this might be stationary or mounted on a robot. Here they're using a touch table as well in conjunction with that projection. And so they're able to manipulate the virtual images on the table. There's also static screens. So you might be sitting at a computer terminal, and it could be remotely, it could be in the, co-located with the robot. I have this category I call alternate interfaces. So these are things like peripherals, such as like a drawing tool or a gesture glove, or in one of the papers I read, they use a tongue drive system, which is kind of cool. You can use your tongue to manipulate objects in the space. And then there's certainly literature that compares different types of AR and combines them as well. So the main categories that the applications fall into are listed here. These are kind of what most of the literature falls into. And I'll be picking out specific papers from the ones that are bolded here. So that's what we'll be talking about for the next few minutes. So in this paper, you see an AR view of a user manipulating the hologram overlay. So the linkage changes color when it's selected, and this virtual robot is overlaid on the physical robot. So it's kind of hard to see here, but the actual robot is behind it. And the goal is teleoperation. So the user can either manipulate the end effector or the linkages to create the desired position for that robot arm. Their feasibility study explored a bunch of different things, method of generating the robot arm as a manipulable hologram within the HoloLens. They were using a registration algorithm and built-in gesture recognition that the HoloLens has. And one of the issues that they noticed in their proof of concept was that the segmentation issues resulted in the hand tracking not performing well. So if there was a dark background or when it was close to other objects, which is an issue, then it didn't perform very well. So this is certainly an area that can be improved upon for AR technology. This is another industrial application. So a human subject is using spatial augmented reality to program a robot. So they're using this to create the program, and then the robot is then expected to prepare parts for assembly. So the worker is using the AR objects to perform these tasks. So they have like a block program that they can manipulate, which you see in kind of the upper left here. And they can view the object outlines, which you can see down here. So, where the object needs to be placed, they're able to manipulate that in the space. And since all this work is occurring on the table with the robot across from them, so you can see kind of the robot is right here, it's intended to increase focus, increase situational awareness, improve use by novice users, and remove the need for other devices like a head-mounted display that can be heavy or distracting. And then the tabletop system is also serving as input for the robot and feedback for the human. One of the things that they noticed was that this touch-capable table was sometimes either distracting or didn't work as well as they wanted it to. So yet another possible area for improvement here. Another application is for pick and place tasks. So in this In this example, we see a comparison of 3 different types of AR. So we have this monitor, or what I was calling static display. We have this projector, so it's projecting the images down from above. And then this is the view from the Microsoft HoloLens. So these virtual images are being projected in the user's field of view. So the system that's presented in this paper combines natural language understanding and object recognition to disambiguate which objects the user wants the robot to pick and place. So someone might say, choose all of the orange objects, and the system can highlight the ones that it thinks are intended to confirm that that is actually the case. And then in this next pick and place task, we have a smartphone app that allows a user to select an object and a goal location. And that's shared with the tabletop robot manipulator that has this 1 degree of freedom gripper through a central computer. So one thing that's worth noting here is we have these fiducial markers that locate the robot arm in the space. And markers like this are a way of changing the workspace to accommodate the use of AR. This is utilized in a number of different papers that I reviewed. In this case, it's orienting the arm, but it can be used to identify objects, show displays, information, things like that. So the phone app communicates with the robot via that computer using Bluetooth. And then in the AR interface, the user can select the object that it wants the robot to pick up by putting the crosshairs over that object. So these crosshairs that you see in the middle here. They use that to indicate what object they want it to select and then where they want it to go. In the second paper, they expand on that by providing the option for grasping. I think it's hard to tell in these photos, but either grasping from above or grasping from the side, depending on the type of object. So here it's just a block. You can grasp it from above, which is in some ways easier for this particular robot, but this can needs to be grasped from the side. So search and rescue is also another common use for AR for human-robot collaboration. So I'm going to present a series of 3 papers here. All of these papers are using all these experiments use a Microsoft HoloLens and a mobile ground-based robot. So here you can see the different visual aids that are provided. The red sphere is indicating the target location, and then the robot is providing a path for the human to navigate to that robot location or to that goal location. And in these cases, it's kind of behind these walls, so you can see the hologram that is, quote unquote, in the wall. And the robot itself has generated its map of the environment with 2D laser scanning. In this follow-on paper, the green line indicates the path that the robot intends to follow. And the purple line is the trajectory of the robot, the current trajectory. What isn't pictured here are additional images that the robot can provide to the human user that display unexplored areas versus explored areas of the building. And then in this final study, they are including a gesture glove that is used to teleoperate the robot. So they've come up with a series of commands that someone can provide using the gesture glove, and then they're evaluating these commands. There are 3 different environments that they're evaluating in. So this is a subterranean, kind of a subway platform environment. We have a poorly lit basement, and then an office building. And you can see kind of similar images and indicators from that are similar to the previous papers. One of the things that came out of this particular study was that certain gestures are very difficult for different people to make. So when you're using a peripheral like this, you want to make sure to keep that in mind. So next I'm going to be talking about some technical contributions. The ones that I read about really seem to fall primarily into these 7 categories. Intent communication and path visualization are closely related. but I do differentiate between them. So intent communication relates to, we're communicating in robot intent to humans via AR. So path and motion visualization is related, but it's differentiated in that intent isn't always path or trajectory based. So a robot might want to communicate an overall plan or a goal location or just a general intent so that the human collaborator doesn't duplicate efforts, so they don't alter the environment to make the robot's goal impossible, or stay safe, make sure they don't put themselves in danger. So I'll be talking about the bolded categories here. So intent communication, this is one example. We have a human collaborator work in a shared workspace. They're working on this assembly task. We see projection-based AR, and the user can immediately see whether a part is recognized by the system, and it can also be shown if there's a current target for the robot or that object. They can be shown a trajectory path or a swept volume for the robot so that the person can safely move out of the way or know that they're already working in a safe space, even if it might appear as though the robot is moving towards them. And this really builds trust between trust of the robot from the human. So this is a key result of communicating robot intent, is the calibration of a human user's trust that results from their mental model of the system and from an understanding of its capabilities and limitations. And that calibration of trust is one of the primary goals in this particular paper. So they're using this phone-based mobile app. So this is an image of what that would look like on the phone. You can see this tree-like display of the robot's plans and priorities. So this is shown to the human, and they can then see what the intents are, and also be able to debug it, so that this allows for that capability as well. In a study by Walker and others in the Iron Lab, they are using different visualization designs to test for communicating to a human in a shared space. Here they're using a quadcopter robot, and they're testing these 4 different visualizations in this between subject study. So we have nav points here, and it's a little, I think, in this image, hard to tell. There's a line connecting these spheres. So we have waypoints with the path that the robot intends to take. In this design called CAIRO, the arrow actually tracks the robot's path for a given time into the future. So as the robot's moving, so does the arrow. Gaze turns the robot itself into what the authors call a flying eye. So you can faintly see the robot kind of inside this flying eye, and the eye it's gazing at its next destination. And then finally, utilities is providing information to the user in kind of an egocentric or user-centered way. So in this particular image, we see this radar. So imagine the person who's wearing it is the center blue dot, and the location of the robot is shown here with the red dot. So this arrow is saying to the user, the wearer of the HoloLens, that if they look to the right, then they should be able to see the robot. And this is tracking with the user at all times. And then one thing that I like about this is that you will see examples of these different designs throughout all of the literature that I'm talking about. So you probably are noticing some of this represented already, and you'll see some more as well. In this other pick and place task, we have non-experts that were asked to program a robot. And it's using, they're moving printed circuit boards from one place to another. So they're using block programming. So these pucks are the actions that the robot can perform. And then we have these lines that are connecting those actions and showing what order they need to be completed in, and the actual flow of the program. There's also quite a bit of literature on safety and space ownership. So In this image, we see a green volume that shows where it's safe for the operator to work, and then a red volume that highlights where the robot is working. Additionally, there's more information that's shown in this view. So this is the task that they're working on. This is maybe the orientation of an object in the space. So lots of different opportunities for increasing safety. And then there is this image that we saw before from a study where the user can actually restrict the robot's workspace by specifying an area. And here they're specifying the area around the carpet. They can draw this perimeter on the tablet, and then the robot knows to avoid this area while it's working. And it simultaneously, the tablet is providing that direct visual feedback to the user. And then they expand on this and enable the system to actually learn what spaces might be prohibited based on the indication that this is a prohibited space. So in this image with the yellow outline, the system is suggesting that this might be another off-limits space, and the user can indeed select that as off-limits. And then there's lots of other types of visual assistance that can be provided for human teammates. So in this study by Hedayati and others from the Iron Lab again, they're presenting 3 different design methodologies. And these are designs that we can use to design any AR display that we're using for human-robot collaboration. So in this instance, they're implemented using the HoloLens, head-mounted display. We see this fresh room design, which is augmenting the environment. So they're using virtual lines to indicate what is within the quadcopter's field of view. So we can see where the field of view of the quadcopter camera stops and starts and ends. In the call out design, we see this panel that's following the robot around. So as the robot moves, so does this video feed of the camera that's on board. And then in the peripherals design, it's much more egocentric, right? It's centered on the user. So it's tracking the person as they move. So in this case, the image, the live video feed will stay in the upper right corner of the field of view. These design frameworks work really well for situations where the robot is separate from the human, but they're co-located in the environment. So in a study where they asked participants to collect photos of the environment by teleoperating the robot as fast and precisely as possible, these designs generally allowed users to perform better than a baseline handheld device that also displayed the video and allowed for teleoperation. And then in this study, users evaluated different HMD designs for teleoperation of a robotic wheelchair. So we see different types of icons and display modes that are tested. The user controlled the wheelchair from within the AR interface. And then the choice of movement options is shown to the user in their field of view. So here, we can see one is indicating this is the robotic wheelchair. These are different locations on the floor that can be selected. This arrow with the human is to indicate that you can approach this human. You can select all of these options from within the HoloLens. And then they compared this against using natural language, such as just go through these doors that the go through is placed over, or approach this person. So I'm going to talk a little bit about how we do evaluation and how we use these instruments that are meant to evaluate. So as I went through all of the literature, it was interesting to see that the instruments that I've listed here were used a significant amount. Like they came up multiple times, but a lot of them were used in conjunction with another. So you might use the TLX and the Godspeed questionnaire series, or select different elements from each of them. So I'll kind of highlight some of them here and just talk about how they're used. The NASA TLX, or Task Load Index, is perhaps one of the most widespread in assessing augmented reality for human-robot collaboration. I saw it come up many times over. It assesses workload on 5 different 7-point scales, and it's easy to kind of administer multiple times over if you're doing a within subject study, for example. And it's obviously intended to measure like what the workload is, right? The Godspeed questionnaire series is meant to measure humans' perception of robots. So things like anthropomorphism, animacy, likability, things like this are what's assessed in the GQS. And so what I did see here is that certain aspects of this instrument were kind of taken out and used on their own. And then with the user experience questionnaire, again, it's another like ranking. You have different items and you rank them, and the types of things that are being rated are things like attractiveness or efficiency, and this is for maybe a whole system or a new technology that's being evaluated. The system usability scale is a method of quantifying things that are kind of hard to quantify, right? So usability, how usable something is. There's 10 different statements that users can rank, again, from strongly disagree to strongly agree. So like an example might be, I think that I would like to use this system frequently, and you can say how much you agree or disagree with that statement regarding the system that you've just used. So a common claim that papers have made as I've done this review is that AR lends itself to increasing situational awareness, or SA. This can be a difficult thing to assess. The situational awareness global assessment technique was actually developed in 1988, which is interestingly the same year that the NASA TLX came out, to assess aircraft designs for pilots' situational awareness. And they developed this system to where they actually had people participate in a task, and they would pause at various points throughout this task and have to answer a series of questions about their environment. And so the key thing to know about the SAGIT is that it's much more a technique. It is not a particular instrument. It is, you're interrupting the person and asking them questions about the environment, but the questions are going to depend on what that environment is. And so these are some of the common instruments that are used. There are many others, and I think one area that is definitely ripe for further exploration is kind of figuring out how to use these instruments and combine them in maybe more consistent ways. So next, I'm going to talk about the experiment that I have been working on and the questions that I'm interested in exploring with that experiment and into the future. So a little bit to set it up, it's in a shared space environment. I have one robot, which is a Parrot quadcopter, and one human subject. The human subject is equipped with a HoloLens, and their task is to complete an assembly from bins around the room. So this assembly looks something like this, this right here, where it's just a bunch of mega blocks, and those blocks are stored in bins that are distributed throughout the room. The robot's task, on the other hand, is to be completing inventory of those bins while the human is doing theirs. And in order to traverse the space, the human has to request permission from the robot in augmented reality. So what this looks like is you have a human home base, they're here, and you also have your robot home base that they can return to. And in this case, our robot is taking inventory of bin 4. So our bins are these numbered rectangles along the edges. And then the human is seeing in their HoloLens display this, this grid that is lit up with different colors depending on who owns those spaces. So in this case, the robot owns all of these red spaces, and the yellow is designated as no person's land. Then the human decides that they need access to bin 1. So bin 1 has whatever part they need next, and they ask permission. So this blue indicates that the human has now requested permission using their HoloLens to traverse the space to get to the bin that they need. The robot is also simultaneously conducting inventory of bin 5. The human is granted permission to traverse into the space by being shown the green areas here that they're allowed to walk. So anything illuminated with green in their HoloLens is go space for the human. To compare, we're running a turn-taking experiment where the human and the robot are not actually sharing the space. So in this case, the human has permission to traverse to bin 1, but the robot actually isn't doing its inventory at that time. It's returned to its home base, and it's going to wait until the human has left the space and returned back to their respective home base in order to continue its work. So the questions that I'm hoping to answer with this experiment are, how much more productive can a human robot team be when they're allowed to work in the same space and not be forced into this turn-taking scenario? When they're confronted with a regional claim conflict, how does the participant react? So one thing that we will do as the experiment progresses, the human's routes around the space will become more and more circuitous, and they may even be denied access to the space. And we want to know what happens. How does the human react to that type of command from the robot? And then how willing are they to conform to the robot instructions? So if the area that they're given to traverse is not the obvious route to the bin, then are they going to disobey? Are they going to conform? And then in the future questions that I hope this will lead into are, how can we enable humans to function with multiple agents in a shared space? So what happens when we add another drone or another ground robot? And how can we fluently incorporate humans into a multi-agent planner aided by augmented reality? So can we incorporate humans into this whole system and expect them to comply and perform as the system expects? So in order to answer some of these questions about a multi-agent planner and to explore further the idea of incorporating a human into this process, I'd like to share with you a paper that was written by Matt Gombolay, Ronald Wilcox, and Julie Shaw. And I'll talk about the algorithm they present called Tercio and how I might incorporate this algorithm into my future work by expanding on it. So this paper is titled Fast Scheduling of Multi-Robot Teams Performing Tasks with Temporal Spatial Constraints. It was presented at RSS in 2013. The image shown here is from the paper, and it shows an application for this algorithm. So we have these two robots, and they're painting 6 separate sections of this airplane fuselage. So we'll return to this example a few times throughout the rest of the talk. So why am I sharing this paper? Well, I kind of talked about this a little bit already, but it shows it's about efficient scheduling and task assignment, particularly with humans and robots working together, multi-agent teaming capabilities in that shared space. And then I do see potential for incorporating AR to support this collaboration. So the main contribution of the paper is this algorithm called Tercio. It's this task assignment and scheduling algorithm. And it's planning temporally and spatially, right? So we have these different constraints. And it's basically a mixed integer linear program that's been decomposed into these 2 sections of task allocation and task sequencing. And so we'll talk about both of these. So the problem formulation is as this mixed integer linear program. And we start out with this objective function that's application specific, and I'll talk more about that a little bit on the next slide. But the equation 2 ensures that each task is assigned to only one agent, because that's as many tasks as one agent can perform at a time. The equation 3 ensures that temporal constraints relating the tasks are met. So if we have to paint the second coat after we paint the first coat, that's what this is in charge of here. 4 and 5 ensure that agents aren't required to complete tasks faster or slower than they can. 6 and 7 they sequence our actions to ensure that the agents are maintaining buffers. So either if we don't want a human to get too close to a robot for safety, or if two robots can't safely operate too closely together, then that's included here. And then we need to ensure that each agent is only performing one task at a time. So here we have our objective function, and it's broken down into these 3 sub-functions. So function G here is minimizing the difference between our previous agent assignment and our returned agent assignment. So this is as we're going through our iterations, making sure that we're not oscillating between assignments. H function here is minimizing how many spatial interfaces there are between the tasks performed by different robots. So if we look at this image, we see there's only one interface between, the tasks performed by this robot are in the reddish color and this are in the blue. So there's only this one interface. So we want to minimize that for efficiency as well. And then finally, our last sub-function here is minimizing the time it takes to complete the entire process, right? It's reducing our make span. The inputs to Tercio are as follows. So we have our simple temporal problem, which is just our set of all of our temporal constraints. We have our P, which is this binary decision variable that tells us whether or not the agent has been allocated to the task. We have our set of all of our agents, set of all of our tasks, and then this set of all task pairs separated by less than the allowable spatial proximity. So this is where that, if two tasks are too close together to be performed at the same time, they're included in this set. And then our cutoff is our make span that we have to provide to say this is when we stop our optimization process. So with these inputs, we have our Tercio algorithm. As I said, it's separated into this allocation and sequencing tasks. So the allocation is just performed by this third-party optimizer, the Gurobi optimizer, and that's giving back to us our agent allocation matrix. So which agent is associated to which task for all of our tasks and agents. Then with that information, we update our interval temporal constraints. And then we use our sequencer, which I'll talk about on the next slide, but that's returning our optimal make span and then the sequence of tasks for each agent. Once we have all of that, then we can add these sequencing constraints to our simple temporal problem constraints. And this dispatchable just basically, it returns these flexible time windows. So that means if we needed to insert a human into the process without prior planning, or we needed to do something like that, then we have some flexibility there. So our sequencer algorithm takes tau, which actually encodes a few different things. It has our agent assignments, it has our shared memory resource constraints, and it has our deadline constraints. And then it also takes this cutoff that we talked about before. And the first thing it needs to do is sort these subtasks. And it does that using these dynamic priority heuristics. It maximizes how many agents are working at once to make it as efficient as possible. We want all of our agents to be busy. It prioritizes high demand resources so that we're avoiding bottlenecks. We don't end up at the end with a bunch of resources that are all in demand at the same time. Is prioritizing subtasks with follow-on subtasks assigned to other agents so that we're not so that agents aren't waiting. And then we are preferring nearby tasks over distant ones, which is enforcing that minimizing number of interfaces, as well as reducing travel time for our robots. So once we have these tasks sorted, we can use we can do a consistency check, which is just making sure we're not violating our temporal-spatial constraints. And then once we have all of that, we've just run through every task for until we have everything allocated, and we return our task sequence and our make span to our original algorithm. So they did evaluate this using randomly generated programs or problems. The idea was that this is to be used with multiple agents on a large construction project, like the one that the picture that I shared. They had task times in this uniform distribution from 1 to 10. About a quarter of the tasks had a non-zero lower bound, and about a quarter of them had an upper bound that was related to another task. And they drew subtasks and locations from uniform distributions. They ran this on 25 problems, and they used from 4 to 10 agents. You can see that in the graph on the side. And they ran it for 5 to 500 subtasks. And you can see they compared this to this mixed integer linear program benchmark. And even with just 4 agents, it's the completion time is increasing exponentially, whereas Tercio is performing much better, even with 10 agents at 500 tasks. So I'm going to play this video that is an example of Tercio in process. So these robots are just painting, they're quote unquote painting. You can see the different colors represent which robot painted which sections. Now they had to respond to this quality assurance check. And so the first thing that I noticed when I was watching this video is that, let's pause this guy, is that it doesn't include motion planning or collision checking during transit. So you have this great algorithm that does all of this planning, but it's not planning the motion of the robots themselves. So I see that as an area for my future work. So I want to be able to include in that algorithm how the robot's going to get from one position to the next. We can do this by adding constraints to the objective function. We can provide a pre-computation step that accounts for that transit, and then also a heat map so that we can avoid other robots, we can avoid humans in the space, we can avoid any other objects that might be there. So some areas for my future work that I see, in addition to what I just discussed, are AR interface design and interaction protocols, how people interface and interact with the augmented reality technology. Robots and systems that are designed to be collaborative and dynamic, so that the collaboration is designed into the system. Using humans as compliant teammates, which I talked a little bit about before. And then establishing some common evaluation methods. We spent some time talking about evaluation, and I think that's definitely an area that could be really interesting to work in. And then finally, tighter integration with this robotics roadmap that is published every 5 years or so, with some great ideas and suggestions, but it doesn't seem to come up a lot in a lot of the research literature. With that, I'd like to thank you all for coming to my talk, and I welcome all of your questions.
What timing.